So we will start this morning session. So we have this morning only one talk, and after we will have a poster session. So this talk will be given by Professor by Kwashi Tosho. He works at Riken Center for Advanced Intelligence Project in Tokyo, Japan. And his talk is on exponential family by representation theory. Okay, I give you the floor. Okay, you can start.
Okay, thank you for the introduction. The title of this talk is Exponential Family by Representation Theory. This is a joint work with Taro Yoshino. In this talk, we use Lie groups and its representation theory technically, but I will not enter the details of representation theory in this talk. I will try to tell the essence not only to experts, but also to those who are not familiar with representation theory. First, we explain our aim of this research and demonstrate a family of distributions on upper half plane with Poincare metric, so that we can share our aim of this research. Wait a minute, please. Can you see this animation? This is a distribution on upper half plane. In my iPad, in my iPad, the distribution is moving. Okay. And okay. I can check on YouTube. The red line is x-axis, and the green line is y-axis, and the blue line is z-axis. The right side is the upper half plane with Poincare metric. This is a family of distribution on upper half plane with three-dimensional parameter space. If the distribution is close to the x-axis, then it is sharp because of the Poincare metric. Since the right side of the distribution is higher than the left side, so it does not seem symmetric. But it is symmetric with regard to Poincare metric. Our aim is to suggest good families of distributions on important spaces, such as upper half plane, sphere, and hyperbolic space, or more generally, symmetric spaces. Okay, back to slide. This is a plan of this talk. First, I will talk about background and our motivation. Next, I will explain our method. We call it G-modate method here. Finally, I will give some examples obtained by G-modate method and introduce a related work. In the field of machine learning using a family of distribution is one of important methods. Here, learning is mathematically to optimize the parameters in the family of probability measures. We often use exponential families as a probability model. This is a good class of families of probability measures. In fact, exponential families are important subjects in the field of information geometry and useful for Bayesian inference and include many widely used families. These are examples of exponential families. Exponential families include normal distributions, Bernoulli distributions, gamma distributions, Richard distributions, Fermi distributions, and so on. Categorical distribution is a generalization of Bernoulli distribution, and the Richard distribution can be regarded as a generalization of gamma distribution. Fermi distribution on S1 is often used in the field of directional statistics. Here is our definition of exponential family. We modified well-known definition in the field of statistics for convenience to representation theory. Roughly speaking, exponential family is a family of distribution having this exponential form. More precisely, let X be a manifold and Rx the set of all random measures on X. A subset P of Rx is an exponential family on X if there exists a triple mu Vt satisfying the following four conditions. The first condition is mu is a random measure on X. And second one is V is a finite dimensional vector space over R. And the third one is T is a continuous map. And the fourth condition is the most important condition, which says for any P in P, there exists data in the dual of V satisfying this equation. Where phi theta is a log normalizer. We call the triple mu Vt a realization of P. Some texts call this triple representation, but to avoid conflict with group representation, we call realization in this talk. Let's see a typical example, a family of normal distributions. The family of normal distributions is an exponential family in our sense. The family of normal distributions has this form with parameter sigma and m. M is the mean, and the square of sigma is the variance of this distribution. This is an exponential family in our sense. In fact, we can take a realization mu Vt like this. This is not unique, but easiest realization with regard to the dimension of V. Please remark that we can make too many exponential families. In fact, for given the three input, then we obtain an exponential family on X. Your first input is manifold X with major mu, other major mu, and a finite dimensional vector space V, and the continuous map T. Then putting the measures like this, and set the parameter space as an integrable parameter, and consider the log normalizer. Then normalizing the this p tilde theta, then we obtain a probability measure. So by collecting the p theta, we obtain a exponential family on X. By definition, there are too many exponential families. However, only a small part of them are widely used, like this picture. Oh, sorry, it is too small to see. Let's enlarge here. There are good exponential families we often use here. From this picture, we can expect there exist good exponential families. So we want a framework to understand good exponential families systematically. This is our motivation. The following observation gives us a hint to attain our purpose. That is, useful exponential families have the same symmetry as the sample spaces. Mathematically, the sample space is a homogeneous space G mod H, and the family on the sample space is invariant under the induced G action. Here, G is a Lie group, and H is a closed subgroup of G. Writing a space by the form G mod H is mathematically a description focusing on symmetry. So our idea is to use representation theory, which is a theory of symmetry. This is an example of G mod H. Real line can be described as like this, and two-dimensional sphere can be written like this. To attain our purpose, we proposed a method to construct exponential families by using representation theory. In this talk, we call it G mod H method. G mod H method has the following two good properties. G mod H method can generate many well-known families. Moreover, families obtained by this method can be classified. So we can expect that new families here obtained by this method are good. Now, we will explain Gmod H method. First, let us see the method roughly. Later, we will explain the method step by step. Gmod H method is a method to construct a family of probability measures on homogeneous space Gmod H from the following two inputs. One is a finite dimensional real representation rho from G to GLV, and the other one is a non-zero H fixed vector V0 with regard to this representation. Here, GLV is a group consisting of all linear isomorphisms of V. We will see the details of Gmod H method step by step later, but roughly speaking, we take the following 5 steps. In step 1, we take Lie groups G and the closed subgroup H of G and consider homogeneous space X of this form Gmod H. We denote denoted by X here. Then X is our sample space. In step 2, we take two inputs, finite dimensional real representation, rho V, and H fixed vector. In step 3, we consider the set omega GH of all non-zero relative region invariant measures on X. In step 4, we make measures parameterized by direct product of the dual of V and omega GH. In the final step 5, we normalize them. Before moving to each step, let us see examples obtained by Gmod H method. Our method generates useful families of distributions systematically. In fact, by choosing this input, GH, V0, we obtain these families of distributions. Choosing input GH, V0 is to give an interpretation of symmetry of the family of distributions. We remark that these are not all of examples obtained by our method. To explain each step of Gmod H method, we would like to apply Gmod H method to construct normal distributions in the top of this table. Now we enter the details of Gmod H method. In the left side, we explain each step in representation theory. And in the right side, we explain each step, we demonstrate how the family of this normal distribution is generated by Gmod H method. In step 1, we prepare a sample space with symmetry. In the representation theory side, we take a Lie group G, which describes a symmetry, a closed subgroup H of G, and the homogeneous space G mod H, denoted by X here. In the normal distribution side, R has symmetry of scaling and translation. So we take the corresponding semi-direct group G and its closed subgroup H like this. Here, the first component represents the scaling, and the second component represents the translation. Then we can identify G mod H with real line via this map. We reconstruct a family of normal distributions on R with the well-known form. In step 2, in the representation side, we give inputs to generate distributions. We take a finite dimensional real vector space and representation law from G to GFV and non-zero H fixed vector V0. Here GFV denotes the set of all linear isomorphisms of V. In the normal distribution side, we take the 3 inputs like this respectively. Here, C2R is the vector space of all symmetric matrices of size 2. Two checks V0 is H fixed. Let's consider the case where X equals 0, goes to 0. Then we can check, check that V0 is H fixed with regard to this representation. In step 3, we consider measures compatible with the symmetry. In the normal distribution side, a measure compatible with scaling and translation is essentially the Weg measure. Mathematically, measures compatible with symmetry means these are relatively G-invariant measures. Here, the definition of relatively G-invariance is given in definition 2.3. That is, a random measure is relatively G-invariant if there exists a continuous map from G to the set of positive real numbers, satisfying this random Nicodemus derivative equation. Then this map chi is automatically group homomorphism. So we consider, in the representation side, we consider the set of all the non-zero relatively invariant measures on X up to positive gamma. We denote it by omega GH. This depends only on the pair G and H. This does not depend on the representation law. We regard an element omega GH as a parameter later. In step 4, we construct measures on X with symmetry. More precisely, in representation theory side, we define measures parameterized by the direct product of the dual of the vector space V and omega as follows. Here, rho is abbreviated, and this is well defined. This notation is well defined because V0 is H fixed. In the normal distribution side, by taking natural inner product on V, then we obtain measures parameterized by real numbers, theta 1, theta 2, theta 3, like this. In the final step 5, we normalize the measure above. In the representation theory side, we denote by large data the set of parameters such that the measure is integrable on X. We call it parameter space in this talk. Then by normalizing the measures, we obtain the set of probability measures P data parameterized by parameter space. Here, phi theta is a log normalizer. In the normal distribution side, we can compute the parameter space and log normalizer and P theta like this. Namely, we obtain a family of probability measures on R as shown. Moreover, by changing variables here, we obtain the well-known form of normal distribution. Now, we see the properties of G mod H method. The family obtained in this way has good properties. Namely, the family obtained by G mod H method is a G invariant exponential family on G mod H. For example, in the normal distribution case, G action means scaling, and translation. So this proposition corresponds to the fact that the distribution transformed by scaling or translation from normal distribution is also a normal distribution. Then the following question 2.5 naturally arises. That is, conversely, are any G invariant exponential families on G mod H obtained by our method? The answer is yes, under mild assumption. So if we accept the answer, roughly speaking, we get the following diagram. That is, there is a correspondence between the set of gene-variant exponential families on G mod H and the set of families on G mod H obtained by G mod H method. Let us see the answer to question 2.5 more precisely. We consider the setting 2.6, that is, P is a gene-variant exponential family on G mod H. Here, large data is a parameter space. Then we obtain the following theorem 2.7. Let's assume the following two conditions. The first assumption is G mod H admits a non-zero relatively gene-variant measure. And the second one is large data is open, parameter space is open. Then P is a subfamily of a certain family obtained by G mod H method. The first assumption is necessary because G mod H method uses a relatively gene-variant measure in step 4. The second assumption is necessary because we consider the continuous setting. We do not give a proof of this theorem in this talk due to the restriction of time. If you are interested, please see our paper, which will appear in information geometry. From now on, we consider a classification problem of gene-variant exponential families. Let us consider an important homogeneous space G mod H, such as a sphere and a hyperbolic space, homogeneously symmetric spaces. One of our aims is to classify good exponential families on G mod H. From our perspective, good means having symmetry. So our problem is to classify invariant exponential families on G mod H. By theorem 2.7, this problem above is reduced to the following question 2.9. That is, classify families obtained by G mod H method on G mod H. As a first step for classification of the invariant exponential family, we consider question 2.10. Please remark that these distinct pairs of representation and H-fixed vector can the same family by G mod H method. So our question is, when do distinct pairs generate the same family? Here V is a representation and V0 is a H-fixed vector. To answer this question, we introduced an equivalence relation on the pairs of representation and H-fixed vector. Then we get the following proposition, 2.11, which says equivalent elements generate the same family by our method. Here, we tilde GH defined as follows. Here, V0 is said to be cyclic if the orbit of V spans the whole representation space V. The cyclic condition reduces the redundancy for the classification. The equivalence relation is given as in definition 2.13. That is, two pairs is equivalent if there exists a linear isomorphism such that the image of V0 by phi is V0 prime. We do not give the proof of proposition in the previous slide in this talk. If you are interested, please see this published paper on the method to construct exponential families by representation theory. By the first step, our next step is to determine the equivalence classes. Here, we are writing a paper about this question. Hi, yes. Let's move to the final section of this talk, examples and related work. Before entering concrete examples, let us share our aim here. Our aim is to suggest new useful families of distributions for application by Simultaneous method. So this is our message. If you want a good family of distribution on some spaces, please tell us the spaces. Then we will try to propose good families of distribution on them. Here some spaces mean not only Euclidean space. Here we will consider three important examples of homogeneous spaces: sphere, upper half plane, and hyperbolic space. There are some famous distributions on them, such as Mises-Fisher distributions, Fisher-Bingham distributions, and the hyperboloid distributions. They were obtained heuristically. On the other hand, we can obtain them systematically by using our method. These examples are important mathematically and practically. In particular, hyperbolic space is good target of application of G-modage method because machine learning using hyperbolic space has been very active recently. So good exponential families on hyperbolic space has been desired. We consider the first example, sphere. G-mod-H method works well on n-dimensional sphere. Here, n-dimensional sphere defined by this equation. Since spheres has a symmetry of rotations, we can describe the sphere as a homogeneous space like this. By using a special orthogonal group S O n and S O n plus 1 and S O n. From these Fisher distributions and Fisher-Bingham distribution were obtained heuristically. On the other hand, we can obtain them by using low-dimensional representations, like this. Moreover, by taking higher dimensional representations, then we obtain good families on Sn, which are not so well known now, but appeared in the research by Cohen and Welling. Cohen and Welling submitted a paper to ICML, which is a conference of machine learning. This paper suggests harmonic exponential families on compact group or compact homogeneous space, such as one-dimensional sphere and two-dimensional sphere, and use fast Fourier transform on spheres to perform gradient-based optimization of likelihood for MLE, and apply them to the problem of modeling the spatial distribution of significant earthquakes on the surface of the Earth. Here, they regard the Earth as a sphere, as two-dimensional sphere. Let us see the relation, the method by Cohen and Welling, and G-mod-H method. The paper by Cohen and Welling gives a method to construct exponential families on G-mod-H by using unitary representation of compact Lie group and G-invariant measure on G-mod-H. Please remark that the method by Cohen and Welling is a case where G is compact of G-mod-H method. In fact, in the case where G is compact, relatively G-invariant measure is automatically invariant measures. So by this remark, our method can be regarded as a generalization of the method by Cohen and Welling. Let's see another example, upper half plane with Poincare metric. Upper half plane has symmetry by the action preserving Poincare metric of FL2R. Since the action is transitive, upper half plane has a description as a homogeneous space like this. By using low dimensional representation, we obtain a family of we obtain a good family as follows. This is a family we demonstrated at the top of this talk by using animation. Moreover, by taking higher dimensional representations, we can obtain new families by Simultaneous method. Upper half plane is a special case of hyperbolic space. So let's see the final example, hyperbolic space. Hyperbolic space is defined by this equation. The hyperbolic space has symmetry by actions similar to rotation for sphere. So hyperbolic space can be described as homogeneous space like this. By using natural representation, we obtain hyperboloid distribution, which is researched by Van der Vrienden and Jensen. Moreover, by taking higher dimensional representation, we obtain new families by Simultaneous method. These are references we used in this talk. Thank you very much for listening.
Question? You have to speak.
So it was
Yes.
a very excellent talk. Thank you. And I have two questions. The first question is that you're using a character chi to define the G invariance at some point. And I wanted to know how is the dependence with respect to this continuous function chi, which is the property of being character. And the second question I wanted to ask is that the Borel-Veil-Bott theorem will give you plenty representation of a real G mod its maximal maximal compact. And I wonder if you use this theory because that's, I mean, already available. That's all.
Sorry, I can't understand the first question. And the second question is your comment.
So first question is about the continuous function chi from G to R
Okay,
that you
relativity
define.
invariant.
How is your construction depending on it?
How this?
You define the G invariance through this function chi.
To your question. Your question is
There. See, there is a chi there. There is a chi function. X,
yes.
whatever. Definition 2.3.
Could you give more details for the definition of 2.3?
Yes. This is a Radon-Nikodym derivative.
Can I send you mail about this?
Okay. Okay, thank you. Other question?
Comme ça. Thank you very much for your very nice presentations. My question is short. Can you find Fermi Dirac and Bose-Einstein distributions by your method? Are they good?
Sorry, one more, please.
The Fermi Dirac and Bose-Einstein distribution. Could you recover these densities?
Density, what density? What kind?
Bose-Einstein.
Bose-Einstein?
You know in physics, Fermi Dirac and Bose-Einstein. No?
Bose-Einstein, I don't know the Bose-Einstein.
Okay. We will send you email on that. Okay.
Oh, thank you very much.
Okay. No more question. Okay. Thank you.
Thank you very much.
Thank you. Thank you. Bye.
Thank you very much.
Bye. Bye. Yes, we will distribute it, the slide. I think what could be interesting is to make the link with the Souriau model, because if you see, he has consider, for instance, compact, non-compact. It could be the disk. So this is symmetric.
Yeah, that was my question.
Okay, but you have also, if you consider S3, I think this model could not be extended to non-null cohomology. On null cohomology. And if you remember the Souriau model, you have exponential 1 g beta. And in fact, if you remember for the Gaussian, he has used a change of parametrization. So I don't remember sigma is equal, I don't remember, theta 1, theta 2, don't remember. But so in fact, it used the inversion of this function, because q is equal to around phi around beta, so it's the function of beta. And in fact, beta is, you have to invert this function to express according to the statistical moment. And you put that here, and you recover the Gaussian. But I think that the Souriau model, with the Souriau cocycle, can address more general cases. But it's very interesting to use this. Just to prove that the Souriau is above. No, but I was very impressed by the work of Tojo. I met him in Tokyo University and then he come back at GSI, and it's very interesting. Very young. I think he has just finished his PhD at Tokyo University, and now he has a Recon laboratory. But it was the object, all the symmetric space. It was the main objective of Élie Cartan and Jean-Louis Cossoul to characterize this geometry. And what we call the the second Cossoul form is in fact the Fisher metric. Is related to the Fisher metric. So for what they are looking for, Élie Cartan and Cossoul, they are this space are many automorphisms. They are looking for forms which are invariant with respect to these automorphisms. example, for the upper half plane, the automorphisms are this one. Okay. So they were interested by this kind of spaces. So you have a question at the end of one paper of Elie Cartan. You have a question. And the PhD of Jean-Louis Cauzoul was to solve this problem of Elie Cartan. So he made his PhD with Henri Cartan, but he solved a problem of Elie Cartan in his PhD. And so he has one of his PhD students was Jacques Vey also. So in a paper of Jacques Vey, you have also some very interesting work related to that. And Jean-Pierre François is a PhD student of Jacques Vey. So you have a direct... Okay, thank you. So we have now a poster session. For this morning, for lunch, we will have sandwich at the restaurant. 5 people have not paid, so Barb, Goffredo, Domatob, Malago, et Volpi. Yes, at the entrance, you have a form. If you want some taxi for Friday or before, to go to Les Houches station or Saint-Gervais station, you have to write your name on the hour that you want a taxi. So the blackboard at the entrance of the building. Thank you.